All right, welcome back for another episode of Con E352. This is the mechanical class, and also today we're going to be discussing calculating heating load. So you're going to need a few things to get the most out of this lecture. One, you're going to need the lecture notes. Two, you're going to need the lecture slides on heating loads. It'll say something like HVAC03. Heat load calculations, and then you're also going to need the handout again, those pages out of the book that I copied for you. All right, so let's get started. We're gonna calculate what we call the heating load calculation. All right, so the heat load calculation. So once we figure out the R values and U values for a building, we need to do something with this. I mean, the point of all of these calculations isn't just calculations for the fun of it. We're trying to solve a problem. We're trying to buy something. We need to purchase some equipment, and we got to know what we're buying. So the whole point of all these calculations is to ultimately get into system selection. So once I know the capacity that I need for whether it's a room or an entire building, now I can go about picking equipment, but equipment comes in the second part of the class. So the first part right now is calculations. So let's continue on with the calculation. From yesterday, we discovered the equation Q equals UA delta T. We use this for any time we've got a difference in temperature and some barrier in between. It's hot outside, it's cold outside, whatever. If I'm going to have heat transfer across something like a wall, a roof, a piece of glass, I'm going to use UA delta T. Don't forget, the U value is just the inverse of the sum of the R's. Now, we didn't really talk about windows and glass last time, and glass is a very important component of the building exterior with regards to energy efficiency. We talked about like an old wall for an old elementary school or brick building, might be as low as, just under 4. Well, that's still way better than most pieces of glass. If you look at like old single pane pieces of glass, Town Engineering, and we looked at the U value for those, that's going to be it's right around 1, which means it's an R value right around 1. Which means it's not doing much at all to stop the heat transfer. Probably a piece of cardboard would be better than the glass that we have in Town Engineering when it comes to stopping heat transfer. But if we were to look at new windows, at a minimum, you'd want a double pane glass and it'd probably have a U value of 0.5 or better. All right, so that's almost twice as good. U values can get very, very low. We can add coatings and tints to it. We can put a third pane of glass in there, etc. I mean, we can get U values on windows. I've even seen some that were at 0.1, which is an R value of 10, which is amazing. However, that particular window was incredibly expensive. It was a triple pane piece of glass, insulating glass with coatings and the whole thing. But it was, I want to say, almost $100 a square foot for that window. So it's possible to get down to those levels. However, once you go from, say, a U value of 0.3 and better, start getting into pretty expensive glass. So just know that. Now, in your careers, that's going to become more and more common. As energy efficiency requirements increase, you're going to see the need for better and better and better quality glass just constantly. So just know that those exist. All right. Now, let's talk about another type of heat transfer. Infiltration. Infiltration is when air leaks into the building through the exterior. Once again, Town Engineering is a great example of a bad example. Air leaks through the exterior walls of Town Engineering like crazy. And with it comes its problems. And by that, I mean, this is air that we are not bringing in on purpose. That's ventilation air. The same equation, but ventilation air we bring in on purpose and we control it. Infiltration sneaks in around windows and leaky walls and doors and that type of thing, and it's a problem. Now, the equation for any time that we have air streams that are mixing and they are different temperature, the heat transfer for that is Q equals 1.08 times the CFM, that's cubic feet per minute, times the delta T, the difference in temperature between those two airstreams. So if I've got a room at one given temperature, like 72, and cold air is coming in, I can calculate the effect, the heat transfer, how much energy we lose because that cold air sneaks in. Now let's just take a look at that. Anytime I give you an equation with Q, know that that is a rate in BTU per hour, a British thermal unit. A British thermal unit is about the same amount of energy as you get from burning like a long wooden match completely. That's about the same amount of energy, right? So Q is in BTU, but it's in per hour. CFM is in cubic feet per minute, and the delta T is in degrees Fahrenheit. You're like, wait a minute, how do I get cubic feet per minute times difference in temperature in Fahrenheit and get BTU per hour? The way we do that is this constant right here, 1.08. 1.08 is a constant that makes all those units work out. If you know how to apply this equation, Q equals 1.08 CFM delta T, you're about halfway to passing the PE exam for HVAC, in all honesty. But applying it can be the tricky part. Now, notice on this equation and the previous equation, you don't see any positive or negative values. You just see a difference. Yes, some instructors get very focused on sign conventions. You know, like a force downward is a negative on a beam. I don't know. I don't even know what the convention is. And I'm not going to get focused on, is that a positive heat transfer, negative heat transfer? Because my experience is if you memorize those rules, you don't actually think about what's going on. Here's how I want you to think about it. I don't want you to think of, is that heat transfer positive or negative? I want you to think, is that causing the room to heat up or cool down? Is it a gain or is it a loss? What kind of equipment am I going to have to use to offset that particular heat transfer? So I want you to say that once we multiply out, let's say that's 100,000 BTU per hour of a heating load. A heating load means we lost energy and I've got to heat the room up to offset it. Here, next week, we're going to get into cooling loads. In other words, there might be hot air coming in and warming up the space, and that represents a cooling load. Is that a heat loss, a heat gain? Is it a cooling load or an air conditioning load or a heating load? That's how I want you to think about it. Focus on the problem solving, not necessarily just memorizing sign conventions. All right, a couple other things here. Cubic feet per minute of outside air. Estimating infiltration is very difficult. The problem with that, with estimating infiltration, is the first word. It's an estimate. A mechanical engineer is going to calculate and size the heating systems and the cooling systems long before the building is ever built. And you don't know what the infiltration rate really is going to be. There's no way of knowing that ahead of time. There's no calculation that you can do, and it's very difficult to estimate it. Common infiltration rates for buildings could be anywhere between, here, notice this, a quarter of an air change per hour or 2 air changes per hour. An air change per hour. One air change is the entire volume of that room. So if you know the air changes per hour, you just got to say one air change is the entire volume, and that volume can be expressed in cubic feet, and then you just have to convert from minutes to hours. We'll do an example on this, so hold on. But the important point here is that infiltration is totally a crapshoot, and you don't know what it's going to be until after the building is built. And this becomes pretty important as we look into our calculations a little bit later. All right, and then delta T, the difference between the inside temperature that we're trying to maintain, probably about 70 or 72, and then the outside air temperature, the air that sneaks in around the windows, doors, and etc. And in winter, we're probably going to assume that's like -10, or someone that's really cautious like myself would probably assume that it's -20 degrees outside. All right, now common infiltration rates. I just got this from this is a way oversimplification for how to calculate air infiltration rates. There's table 2.7 in your handout that talks about infiltration through double hung wood windows in CFM, or I'm sorry, cubic feet per hour per foot of crack length. Yeah, ignore all that crap. Okay. If there's any mechanical engineers in here that have taken the HVAC class and in the ME department, and they had you calculate crack lengths and stuff like that, those are even worse approximations than just trying to guess using these values. Here, if you have a building and it is neutral pressure, in other words, the inside of the building is same as the pressure of the outside, we could make some generalizations on, is this poor construction, tight construction, average construction? And the way I do this anyway is that you won't really know if this was poorly built till after the fact, but what you can do is you can make some guesses and hedge your bets. If we have a building that has a whole bunch of glass, that means there's tons of gaskets and tons of joints. I'd at least start out at average, maybe even poor in terms of how tight it is. If we have a building that is masonry, once again, masonry building is all joints, average to poor perhaps. If we have a precast building, in other words, there's not that many joints, I'd probably take a look at maybe a tight construction. Now, is the building neutral or is it pressurized? Most buildings, we're going to try to give a slight positive pressure by bringing in more outside air than we exhaust. At least that's the goal. And if you do that, you can get some pretty low infiltration rates. I would never start as an assumption that it is 0 air changes per hour. I would not make infiltration 0 no matter what. But you might use some of the lower values if you're a pressurized building, especially if you think it's precast or something along those lines that has few joints. Notice we don't have negative pressure. We should never try to build buildings that are negatively pressurized. However, if you ever walk into town engineering, you open the door and you feel the air rush by you and maybe some of those ceiling tiles jump up. Town is horribly negatively pressurized. It has to do with our lab exhaust system that we added years and years ago. Town engineering added more lab exhaust to get rid of the stinky smell. And yes, believe it or not, town engineering used to be a worse building than it is today. It used to smell like a sewer because of the experiments on wastewater treatment that is done on the first floor. Used to smell like a sewer, so we increased the exhaust. However, bringing in more outside air to offset all that exhaust was not in the budget. So we exhausted and we made our building negative, and now we bring air in like crazy, causing it to have an infiltration rate, if I was to guess, probably at 2 air changes per hour or less. And the reason I'm pretty confident of this is that years ago, our department chair brought me the energy bills for town engineering. I do energy studies for a living. In addition to teaching, I do a lot of engineering consulting, and one of the main areas that I do it in is energy studies. So my boss here, the department chair, knew this and brought me the energy bills for the building and said, "Hey, Brad, what do you think of this?" And I looked at it, and it had the total energy consumption for a period of time. And I looked at it, and I kind of did some math and figured out dollars per square foot per month. And it came, about $1.50, almost $2 per square foot. I'm sorry, per month. It came up to $1.50 to $2 per square foot. And I thought I was looking at the yearly bill. So I told my department chair, I said, well, that's not as bad as I would have thought. I mean, you're under $2 a square foot for a year. And for a lab space, that's not great, but it's not unheard of. I would have thought it was much higher. And he said, what do you mean per year? That's for the month of November. And I was like, excuse me, this is the energy this building used in 1 month, not a whole year. And he's like, yeah, this was just the bill for the month of November. And I said, it can't be. This can't be right. He goes, no, swear to God. That's the printout I got from facilities. And I said, as a taxpayer, I am offended by this building. So just know that once you negatively pressurize a building and you make it negative, there's no limit to how much energy and how much money that is going to cost you. Town engineering building is bad, but probably a worse building is black engineering. Most falls, black engineering is able to pull leaves in from the outside, and town engineering can usually get those leaves up the stairwell to the second floor. But black engineering has been known to be able to pull leaves up to the third floor and maybe even the fourth. So even though town is bad, we're not the worst, and that's probably black engineering. For this class, on a homework or an exam, if I say something like, this is a neutral building that is of average construction, that means you need to look this value up. I will not tell you this value. You need to know where to find it. So make sure that you have these numbers handy for, the first exam or something. All right. Now, ventilation, different from infiltration. Ventilation is air brought in on purpose via the mechanical systems. The cubic feet per minute of ventilation air we actually have simplified in table 2.9. All right, and notice, now this table's a little bit complicated, and it's changed since I originally made these slides years ago. You'll notice that the office space, if you go all the way to the far right column, and that's the one I want you to use. The far right column is in CFM per person. The column to the left of it is occupant density. In other words, we're assuming a certain number of people per 1,000 square feet. If you don't know how many people in a space, use this value. And then you use the CFM per person next to it. The other two columns further to the left, people rate and outdoor air rate, those are meant that if you know exactly how many people in there, you might be able to lower that ventilation a little bit, but you still need to have an allowance per person and an allowance per square foot of floor area. The easiest thing to do in this class is to use the far right column all the time for CFM per person. And for office spaces, this value of 20 CFM per person was from a previous version of this table and of the code. So right now it's for offices 17. So use 17 CFM per person for office spaces. And then like for classrooms, you'd use 13 CFM per person. See where it is age 9 plus. Now, let's say that you had a lecture hall, you could get away with 8 CFM per person. And now you might think, wow, that seems kind of bizarre for a lecture hall with adults in college. But, one thing that a lecture hall assumes is that unlike, say, a elementary school or a high school where the students are in a classroom, the same students in the same room all day, a lecture hall probably only has those people in there for an hour. So they come into the room, they're there for an hour, and then they leave, and that it's used intermittently during the day. So use that one. All right, use that value for lecture halls, for example, for your final project. All right, and then assignment for next time. I want you, don't worry about reading. The only reading in this class you have to do is in the handouts. But the homework 1 and homework 2, as soon as I'm done with this lecture, I'm going to post them. I'm going to post them on the website, and they will be due in 1 week. So they are due a week from today. That's Thursday, due at 2 p.m. And you need to email them to me. And just hints, make sure that you label on the, in the subject matter, label what it is. Put your name, because what I'll do is I'll turn around and send those to my grader. Make sure your name is on that submission. I mean, actually on the piece of paper that you scan in, so that, and I suggest do it in paper, scan it, do it on engineering paper so it's neat, and then scan it, put your name on the top of it, because my grader will probably just print it out and then go that way. All right. Now, I want you to switch over to the lecture notes and the handout lecture notes and go to page 17. All right, we've already talked about these equations, so I'm not going to reiterate those. Okay. Let's go down. We're just this equation. This next one, this humidity equation, we're going to use that when we get to air conditioning. So don't worry about that one for right now. We're going to talk about it later. All right, here's that ventilation equation, 1.08 CFM times the difference in temperature. And let's go to, there's those infiltration rates again. Okay, and then once again, remember that 20 CFM is really 17 now. And let's go to an example. Let's work through an example here. All right, so let's say that we have a room. And let's say that only 2 of those walls are exterior. Think of this as like room 322, except pretend there's a roof on it. I want to do heat transfer through the roof as well. So I've got interior and I've got another interior wall. These 2 are exterior. And let's say that it is 20 foot by 40 foot. Let's do some assumptions. Let's assume the interior design temperature is 72. If I don't say, always use 72, but maybe for an exam or a homework, I might change it around, see if you're paying attention. And then the exterior design temperature is minus 20. I like using minus 20. Some engineers might call that a little overly cautious. However, the last few years have shown us that it could easily be minus 20 here in Iowa, and it could be minus 20 for a few days. All right. Let's assume that those walls are 12 foot high. Like I said, only one of each wall is exterior. Let's give the R value of those exterior walls an R value of 12. I mean, not awesome, but not terrible either. It's not like an old elementary school. Let's give the U value of the glass 0.5, so it's at least double pane glass, and it's okay, not awesome. An R value of 12 is okay, not awesome. 40% glass on the windows. I put 40% because Energy Code only allows you to do 40% glass maximum on an exterior building without offsetting. If you have more than 40% glass, you're going to have to offset that extra energy use with improvements elsewhere. Like it's got to be much better than a code minimum piece of glass. You might have more efficient boilers and chillers and lighting systems, those types of things. All right, I gave you the air infiltration rate of 0.6 air changes per hour, which we said is a rough approximation. All right. Now, notice the outside air temperature is minus 20. Like I said, I'm being cautious. That's not wind chill, though. Wind chill is only felt by people. It is not felt by buildings. Wind chill is just that the faster that wind blows, the faster your body loses energy, and that's why it feels colder. All right, but we're going to use real temperatures. Inside temperature is 72. Let's go through the solution. All right, the way that you approach this. And notice I wrote each of these out. I want you to do that for your homework and for the final project so we can follow it along and check your work. Equation, UA delta T. The U value for a wall is the inverse of the R, so that's where we get 1 over 12. Next, 60 by 12. The total length of those walls is we have a 40-foot wall and a 60-foot wall. At the worst time, it's at night, and it's got the same temperature across both walls. So let's just call it a 60-foot wall that is 12 foot high. Now notice the next 0.6 value. That means that exterior is 60% wall, 40% glass. Next is the delta T. It's 72 inside. It's negative 20 outside. So we multiply those out, and I get 3,312 BTU per hour. In this class, you do not need to go more than 4 significant digits. I do not want to see an answer that's 3,312.4625839 BTU per hour. And the reason is, let's not attribute our answer to a higher level of precision that's possible, and you can't buy equipment that's accurate anyway. All right, so no more than 4 significant digits, please. All right, so Q for the windows, UA delta T, same equation, same area, but times 40% glass on that exterior. Same delta T, and we get 13,200 and some change. Q for the roof. We made the roof R value back up here. The roof R value is 25. The area of the roof in plan view is 40 by 20. We didn't mention anything about a skylight, so it's 100% roof and 0% glass, and we multiply that out. Next, let's go down to the infiltration equation. Remember, write the equation you used and then write out all the individual pieces. 1.08 CFM delta T. All right, but we didn't give it in cubic feet per minute. I listed it in air changes per hour. So I have to multiply that by the volume of the room. That's what this is. 1.08 times the volume of the room, 20 feet by 40 feet by 12 feet, times 0.6 air changes per hour. That gets me cubic feet per hour, and then I need to change hours into minutes, same 92-degree delta T, and now we have 9,538 BTU per hour. Now, something important to notice here, this infiltration is a total guess. Let's back it down to 0.3, right? I mean, now look at the magnitude of these numbers. Just calculating the numbers is important, but I also want you to think about the magnitude of the numbers. Each of these U values is like so-so, okay, but notice the roof is easily the smallest value. Walls are a little bit more, but not a whole lot more. But look at the glass, 40% glass, and yet the heat loss through the windows is somewhere between 4 and 5 times that it would be for the walls. Windows dwarf the other two items. However, look down here at infiltration. Infiltration isn't as much as windows, but it's easily more. It's almost double the combined total of the walls and the roof, meaning that this is very significant. And remember, it's a guess. You could easily be much less, but also, remember town engineering example? Town engineering is probably at least 2 air changes per hour or worse. Look at that value now at 2 air changes per hour. It's worse than everything else. And it's almost worse than all of them combined if air changes per hour was actually 2. That will have a drastic impact on your building, on your comfort, and on your energy consumption. All right, notice down here, ventilation. Now, ventilation is the air that we bring in on purpose. So while these other numbers are significant, and these are what we would call space loads, they directly affect the temperature and the comfort of the room, the space, where the people are. Ventilation air we bring in at the air handler. Like, for example, with a central air handler at Town Engineering, all that ventilation is brought in up on the penthouse at the mechanical unit. Now check this out. If this is a classroom set up the way it was before COVID, and we had 60 people in there at 13 CFM per person, that's 780 CFM of outside air just for ventilation for the occupants. Check out how much energy that we are consuming there. It dwarfs everything else, including ventilation. Now notice, maybe though for that same area, what if this was an office? Yes, if this was an office, we'd have 17 CFM per person. But if it was an office space, maybe it's only 5 people in that 800 square foot area. So that ends up being drastically different. And here's some important takeaways from this. All right. Infiltration is an estimate. Hopefully, we're basing it on experience. Ideally, we want the infiltration going outwards, a positively pressurized building. Leaky buildings can lead to lawsuits. I've got a case study that I want to go over, but I'm going to wait until we go through the cooling loads before I hit up the case study, because I think this will become even more important once we go all the way through the all the calculations. So stand by for a case study, but not this week. Right? Infiltration. Okay. If you're wanting to save energy, I'm going to suggest get better glass and seal up the building. In other words, caulk. Those are, if an owner is looking to me and saying, hey, I want to save energy, where should I spend my money? The best bet is not, let's just add some insulation to the roof or the walls. Your best bet is to cut down on your infiltration and buy better glass. All right? Some other items. Through the building envelope, if we ignore infiltration, most heat transfer comes through windows. More glass is more energy consumption. That is always, always, always the case. All right. More ventilation is costly. Complying with ASHRAE Standard 62 is difficult and necessary. Especially these days, as we're looking at people in conditioned buildings, and now we're worried about the spread of coronavirus. That's going to require more ventilation, not next, and then that is going to use more energy and therefore more money to do it. However, ventilation is required by law. ASHRAE Standard 62. ASHRAE Standard 62 is one of the standards that you should know for this class. ASHRAE Standard 62 gives us the ventilation rates per person. It is a standard produced by a trade association, but almost every state has adopted it by law. In other words, now it becomes a code when the building code says, you know what, that standard is such a good idea, we're going to require it. We're going to require it as a part of the building code, and that's what Iowa has done. They've incorporated it by reference into the building code, so you have to do it. All right. Notice we didn't talk about heat from like lights and people. We do not take them into account for heating loads. We are definitely going to take them into account for cooling loads. Lights and heat warm the space up, but we don't take credit for them. We don't take credit for them during heat calculations because we can't count on them always being there. The worst case heat loss is probably in the middle of the night, and it's probably like on a weekend in the winter, in the dead of winter, when the building is empty and all the lights are off. So we need to calculate design heat loss for the worst case scenario to buy equipment for, and we do not take credit for lights and people. We're going to include them when we get into cooling loads. All right, a couple of other important terms here. Notice space loads versus coil loads. Space loads are all these things. Heat transfer from walls, windows, roof, infiltration. Those are all space loads. They directly affect the temperature in the space. A coil load is all of that stuff plus the heat loss from the ventilation that we bring in on purpose up at the air handler. And that gives us our total coil load. In other words, the maximum amount of energy that we've got to add to a building to offset all of the heat loss. All right. So we're going to continue our discussion. Probably next week we're going to do some case studies, and also probably next week we're going to get into air conditioning. Now, do me a favor. Here's what I would like to do for Monday. I got through the entire calculation, the lecture for heat loss today. What I would like to do is go over any questions. If you could send me questions over the weekend, I want you all to try the two homework assignments over the weekend, and then send me questions. And what I will try to do is in the lecture on Monday, answer them all at once. If I don't get any questions, or the questions don't take very long, I'm going to move on to cooling loads, and we'll try to get ahead a bit, and then I can do some more case studies and stuff on Thursday. So stand by for that. Stand by for homework. I'm going to post all of this soon, and by the time you can watch this video, the homework will be posted to Canvas, and I'll have it in an announcement. All right. Thank you very much for your attention, and let me know what you got for questions so I can answer them on Monday.